that in the ones that I was just showing, you evaluated a plan and obtain a value. Evaluate the plan and obtain a value. Here, using lex, you don't do that at all. You obtain the values, and then based on the values you obtain, you actually decide which plan is better. Okay, so the lex actually wants to say something like this one has more priority. So the first one is the highest priority, the second one is the second highest priority, and so on and so forth. Okay, so if you take two plans, P1 and P2, what you will do is that you will evaluate each of the preference formulae. For each of them, you will obtain a value: best, really good, whatever. Okay, and then you generate this vector. Okay, and you decide which one's which by just comparing lexicographically between these things. Okay, and then they have this lexi-mean that I decided to not explain. But what they do there is that they generate this very same vector, and then they order it from best to worst, and then they apply lex. Okay, so and that sort of goes with your intuition. I would like to have a lot of them satisfied, but then yeah.
And there's other problem with that probably, like one best and 7 really really bad is better than all really good, for example, which I'm not sure is the right way to go about it. Yeah. Yeah. So I think choosing the right aggregator is. Yeah,
I think it is my belief that this language is already quite redundant in a way. I think you can express things in the same thing in kind of different ways, and I'm not sure you can express what you said. I mean, have some sort of finer trade-off between.
But then it becomes.
Yeah, then the sum only works for numeric, and then you have to make sure that you don't go over the limit. It's anyway. And I was asking one of the authors, Christian Fritz, whether or not he understood what was the relationship between this kind of comparisons and the ones that you would obtain would be able to write down with TCP nets, and I don't think people have actually thought deeply about that. So there's no. I mean, I think they have some understanding, but not. They don't really have made a good comparison between this language and TCP nets. Okay, so P-plan is a planner that it's able to plan for this language actually. So there exists a planner for this. It is very simple in the sense that it's. I believe that's even implemented in Prolog, and it does A-star search and uses progression, which is the same algorithm that Batos and Capanza use in ETL plan, to evaluate a formula. And the only reason why they want to evaluate a formula is to compute the heuristics. They have an optimistic heuristic and a pessimistic heuristic. So while they're planning, they are updating sort of the truth value of each of the formulas. And so the optimistic weight, because I skipped all the semantics explanation. What they refer to these things as weights. Okay, the weights are the values, the preference, the values. So they have the optimistic weights, which basically assumes that preference that still have a chance, meaning that have not been proven that they're validated, will be satisfied in the end. Okay. Sometimes you can actually validate because these things are temporally extended. If you say always something and you validate the always, you validate the property inside, you obviously have the thing. You have validated the preference, and they have also this pessimistic weight that turned out to be good for them. And so this one is pessimistic in the sense that it will assume that everything that can be falsified in the future will not be made true in the future. So we won't be able to satisfy anything that can be actually falsified. Anyway, so it uses again this vector. So this is the first priority and this is the second. And because you're using an admissible heuristic here, the planner is actually optimal. Okay. There is an extension of this other planner that I mentioned to you before, HPlan QP, which extends HPlan P for the LPP language, actually for a subset of the LPP language. I don't think they can handle they can handle Lex orders, for example, but it uses inadmissible heuristics, and of course it's not optimal, and it returns, well, if you compare these two planners, HPlan QP will actually return solutions faster because it's not optimal, and will also solve more instances, but they're not optimally guaranteed unless you empty the search space. Okay. Yeah. So just to wrap up with this topic here, we've seen two qualitative preference languages. They both allow you to represent relative importance between preferences, which is what we were discussing extensively. TCP/NET's plan may be incomparable. That's the only thing that I could, actually say that clearly, separates these two languages. I don't want to risk any other comment, but because there's no formal comparison that have been carried out between these two. LPP allows trajectory constraints. That's something that's not directly allowed by the other language. And we just described these three planners. There are two optimal planners, but there are different notions of optimality, and this is not optimal. And so that's it for the qualitative languages. Don't know if there are any questions. Okay. Okay. Promise to be even more intuitive with the last part, which is preferences and HDN. Anyone not familiar with HDN planning?
I wish.
Great. Well, even me, I tend to forget this. I always forget HDN planning. So, no, I guess I won't forget it anymore. But I tended to forget it. Each time I had to sort of review it again and again. HDN, the nice thing about HDN planning is that it is in one way to see it is a way to express search control in planning. So you can, using HDNs, you can define how your solutions look like, and in a way that constrains search for planning significantly, and that in many cases allow you to solve more problems. Okay, so HDNs have been used in the past in planning completions, for example, as a way of providing domain control knowledge, controls knowledge and search control, and therefore provide a mechanism to find solutions faster. Okay, what HDNs are actually doing then is expressing how solutions look like, and you could think that that's what actually people do in a way, or you could argue that that's what people usually do now. They have sort of like schemas or sort of ideas of how these planning problems are solved, and while they're constructing a plan, they're just trying to instantiate this sort of schema in a way. Okay, and the HDN is a hierarchical way of representing the schema. Okay, so for example, you can have in a travel domain, you can specify. The HDN specify how the tasks are achieved. So if the planning task is make my travel arrangements, what the HDN can express is things like, okay, if this is the task, then I have to do these two things: book the transportation and the accommodation. Okay, and to book the transportation, then there are many options. Okay, and to book the accommodation, then there could be many options too. Okay. So one can think that if you go to a travel agent, like the old style travel agent, they would have a very good idea of what all plans look like. They all have a certain structure. Okay? And you could think that this structure can be represented as an HDN. Okay? And then, again, if you go to a travel agent, the travel agent sort of knows how to solve the problem for you, to arrange your travel. But then if the travel agent is a good travel agent, then it will try to consider your preferences. Okay, right? So so that it will provide you with a solution that is decent enough for you. Okay, so that's basically the idea of mixing HDNs and preferences. You have the schemas of how to construct plans, and you want to define a way. You want to define a way in which you would produce plans that are good for using. Okay, so an HDN planning problem is the definition is there. I'm not going to go over that. The idea is that you start with tasks. So instead of having a goal, which is a proposition that you want to satisfy at the end, what you want to do is decompose a task. That's the problem, decomposing. Okay, and generating a plan after you've decomposed everything. So you start with the task, but in this case it's arranged travel. Okay, and the operators here are called methods. That's the way I view it, at least. So you take a task, you apply a method to it, and you generate another task network. Well, actually, this was a task network too, only containing one task. Okay, and you generate this task network, and the objective is to decompose this as far as possible. So now we have to choose another task to decompose. For example, we choose this one, and now we have two possible ways of decomposing this. So here we say arrange travel, book local transportation, book transportation, and book accommodation. Okay, and to book the transportation, we have two alternatives: either go by air or by train. Okay, and this will generate two possible task networks, in which I have replaced this task by this other task network here. Okay, right? Okay, so that's the idea, and you go over and on and on until you just end up with tasks that are primitive. So here the color, I guess pink, refers to a primitive task. Okay, and when you only have primitive tasks, then you're done. And what are these primitive tasks? They're just regular planning operators. Okay, so you actually start off with a planning problem just like the ones you're used. The only difference is that you don't have a goal, you have this network. And at the end you want to end up with a plan that looks pretty much like the plans in regular classical planning, just composed by primitive actions. Okay, so that's the idea. So what is HDN planning and preferences? Well, you just want to have preferences over the results that you've obtained. And then you say to me, well, you know, the only thing you've done is that you changed the way you generate the plans, and now you're talking to me about preferences. And preferences, we've already seen preference before, PDL3. I don't want to know any more about this. And what's new here? Well, I would say the only new thing here is that simply because you're using HDN to represent your plans, you may have a preferences on how to decompose the HDN, rather than only on the form of the plan. PDL3 allowed you to represent preferences on the states that are traversed by the plan, but in the context of HDN, that's only one component. The other important component comes from how you construct this plan, and you may have preferences on that. Okay, for example, if you have a plan here where you book your accommodation and transportation, you may prefer, for example, to buy to use a certain credit card when you're buying your air ticket, and to use another credit card when you're booking some other local transportation. For example, because you get some bonus for using your credit card with a certain airline, some extra miles or whatever. Okay, so the context in which actions are performed, and the context means here actually from what task things are coming from, may be very relevant. Okay, so it's not only preferences about the result, but about things that happen while you are decomposing. Okay, so that's the main difference here, and that's the only thing that. So here the problem is just the same as before, but you want to find a plan that optimizes quality. It's just the preferences that may be a little bit different. Okay, and we skip this. Okay, so and this is an example of what I call here HDN specific preferences. So HDN specific preference, how the user prefers to decompose the HDN, and here's the example of the MasterCard with the Visa. And for example, this one, I prefer rail transportation when travel distance is less than 200 kilometers. Okay, And remember that rail and air were two possible methods. Okay, so at the level of decomposing the network, I choose between some of these depending on the preferences I have. Okay, but really, the context is where the most interesting things can be done. Actually. Okay, so I thought so there are several approaches to planning with hierarchical text networks and sort of HTNs. Even in SHOP 2, the well-known planner, it's possible to specify certain orderings between, possible groundings that you're going to give to an action. So there is a way of representing some kind of limited preference in a way there in SHOP 2. But it doesn't support these HTN-specific preferences that I mentioned to you. And there are these three that do support them, and I'm going to be talking about two of them. And finally, this one here, which actually integrates PDL3, the one that we just saw, with HTNs, but with with nothing more than that. So the preferences are still only about the resulting plan, okay, but nothing about the decomposition. Okay, so Myers in 2000. They had this planner that worked over something that was similar to an HTN, but was not really an HTN as as I described. And they already there, in 2000 had the idea of providing advice. Okay, and the first paper on this, I think it was 96. They had these forms of advice where advice was treated as a hard constraint. Okay. So the idea again was that the hierarchy, the HTN represented some form of solving the problem, and the user, depending on their own requirements, specified the advice. And they had this role advice, which basically I think it could be described as just defining that's the way I find describing the better way I find to describe this was by just saying it's a way of defining which are the arguments that are going to be preferred whenever you are selecting certain methods. Okay, so when you want to decompose, you will have to choose arguments for the methods, and this is a way to do this. Okay, and here are a couple of examples: stay in a 3-star suite hotel while vacationing in Scotland. I took these examples from their own paper. And this role advice is very similar to the PDL preferences on plans. And then the method advice is more like the kind of preferences that I was talking to you about before. So again, they have the same example about don't fly between cities that are less than 200 miles apart, and find a package bike tour starting in Athens for the vacation in Greece. Okay. So that means that when you're in the context of decomposing a plan that involves a travel to Greece and starting in Athens, then in that context I want to satisfy this preference. Okay, and the context has to do with the decomposition. Okay. Okay. So there they had two approaches to deal with these things. They had a set of advices, and what they wanted was to actually satisfy the maximum number of advice possible. So they wanted to find a plan that maximally satisfied the set of advices. And this is obviously a hard problem because if you have a large set, then there's too many options to try. So they had two approaches that were greedy approaches. In the first one, they just, just greedily, whenever they had to make a decision, they took the decision that violated the least number of advices. Okay, that was like the very simple approach. And then they have this local search approach where they find a plan that satisfies a number of advices, and then they try to add another advice, try to find a plan for that. And here, at least a local minimum is guaranteed. Okay. Okay, and then this other guys here, Sarabi and company, proposed a language that it's based on PDL3 but allows you to talk about contextual information. So it is like PDL3, but extended with three things that allows you to talk about contextual preferences. The three elements are these. I'll just explain them to you with an example. Probably the most interesting one is the one. I don't know. So this, for example, the one you see here at last is in the PDL3 syntax, says that you want to sometime after terminate arrange trans, you want initiate arrange accumulation. So here you have a preference of arranging transportation before arranging accumulation, and your initial net could be initially designed to do things in any order. And then here, for example, another condition. Conditional preference. So if the origin is close to the destination, then sometime I want to execute the rail transportation method. Okay, that's it. Okay. The difference between the planner that these guys propose and the planner that Myers proposed is that it's essentially that these guys use heuristics. Okay, so they design heuristics that are tailored to this specific problem where you are decomposing HTNs. And so whenever you're choosing what method to use, they don't decide locally, but they use this look-ahead heuristic, which basically tries to see what's going to happen in the future and simplifying the problem a little bit. I can go into details if you want to, but I know you're tired. So they use heuristics, that's the only important thing, that are specifically designed for this problem. And they use a branch and bound best first algorithm. Okay, so they don't have this local search, but they use best first. Okay, and the heuristics. And anyway, theories are not really that important. Okay, so just to conclude, HTNs is one of the most widely used planning formulas in the industry. Maybe Ron can say something more about that. Extensions and algorithms exist for incorporating preferences, as you have seen. And algorithm, I would say, at least the last one, use sort of like state-of-the-art techniques. And interestingly, however, many authors have shown how to translate restricted HTNs into PDL3. Into PDL. There's a bunch of these authors there. So it's also possible to translate HTNs into PDL. So there's also a question of what is the right approach when it comes to solving these things. It may still be quite natural and useful to represent the HTN because it's how actually plans are being generated. But when it comes to solving, if you can do the translation to PDL, then I don't know if it's worth to construct planners for HTNs, or you should just run cost-based planners. Okay, so there's time for questions here. See you dying.
It's late.
I'm the only one dying.
Yeah. Can you explain the intuition behind that you can develop an automatic delivering translation that can compile from software code, soft codes to hard code without losing any automatically? Or maybe in the worst case, the blow-up will be exponentially that the class you might need to end up with.
Well, I think this is what Jay was trying to explain, and I'll try to explain it, and you correct me please if I'm wrong. So basically the idea is that is as follows: you have a bunch of soft goals, right? So what you're going to do is that for each of these soft goals, you will have a hard goal now. Okay, they're not soft goals anymore, but they're hard goals. But the difference now is that to achieve these hard goals, you will have two possible actions to achieve each of these soft new. If I had a board, it would be easier. But anyway, so there's a bunch of initial soft goals that you now have a hard goal that stands for them, sort of. Okay, and then you have, for each of them, you have two actions. One action that requires as a precondition that the soft goal that corresponds to the guy is satisfied. So if the soft goal is this guy, it will ask for the real goal to be satisfied before. There's one action that does this and achieves this guy, and that requires this precondition. And there's an action that doesn't require that as a precondition, and that still satisfies this guy. Okay, and then you figure out what to do with the costs and what to do with the preconditions so that this works, and which is something that you can figure out. But the main intuition is that you have these two actions, the forgo and the collect. They're called. The forgo is the one that.
Collect?
Oh, the collect is collect. Okay.
I used claim, but
Claim.
collect
Claim.
is
No,
I think
claim.
it is
The claim that actually requires the goal, the sub goal to be satisfied, and adds the corresponding hard goal. And the other one that doesn't have any precondition, well, it has precondition,
It has
but
a negative.
you could think that it doesn't, I guess.
So you have to augment the action set as well.
Oh yeah,
Yeah, that's the part I'm not.
yeah, and then and Jay had an interesting comment about that because they in the Cater and Defner translation they add special constraints so that your
You have to basically
search space won't blow up.
Yeah, you should basically have to satisfy the hard goals, your new hard goals, in a particular order. So one big problem would be that you can imagine, you have all these claim or collects and forgoes, and you have to choose one or the other at every step. So you're now done planning. You have to think, am I going to claim goal 1 or goal 2 or goal 3 or goal 4 or goal 5, all of your goals. So you have this branching factor that's quite big because of that.
I see. Yeah, because I was assuming you stick with the original action space, and I feel like once the compilation is done, and say with the same action space, then it sounds like too good to be true. But now you say you have to augment the action, then everything makes.
So the action has that cost that is actually equivalent to not having the cost.
That makes sense.
The claim and forgoes are only available after the hard constraints are satisfied?
Yeah. I mean, after you're done planning, after you've found your
Yeah. So that's why I said, you have to
Otherwise,
figure out the
the
preconditions so that it works. Yeah.
Are the planners that handle the preferences, are they too new to be used for practical applications, or are there examples where they're being used for practical applications?
You mean the ones that are cheap? You mean all these approaches?
Yeah.
I would say that well, practical applications. You mean real world
competitions.
applications. So no. So if you think that SHOP 2, for example, in the case of the HDM preferences, if you think that SHOP 2 is something that can be used for real applications, which probably is the case, then this planner that I discussed about is built on top of SHOP 2, so it should work reasonably well with.
Can you give maybe some examples? I mean, all I can think of things like scheduling and so on, but I was in the Numberjack tutorial this morning where they talked about job shop scheduling in terms of constraint satisfaction. So I'm trying to get some better ideas for like how the planning is used.
Well, if you want to solve a scheduling problem, I mean, I'm not sure that's the right application for the planner, but
yeah, maybe you can give me better examples.
well, I believe HDN has been used even for like construction planning and stuff like that.
I think the question that you basically, I mean, you could have preferences or schedules, but the preferences on plans tend to be more about the states and the actions, and so in those cases, clearly, any planner which can handle preferences over plans, which is, we talked about those would be more useful. I mean, you could say between multiple schedules, the one, I mean, you could have tardiness versus the resource consumption. Those are two different metrics, and you might consider, which one would you prefer. So you could have preferences or schedules. But here, we spent much more time on preferences or plans. And normally, the main difference that people see between plans and schedules is that scheduling assumes more or less the actions are given, and you're thinking about how to allocate resources for those actions. Planning is only given the goals, and you're trying to decide what actions to put in and what resources to allocate to them. So in a sense, it's sort of more general problem, and so you tend to have more preferences, about how to go about achieving an action, achieving the goal, and to that extent, obviously you need these languages for those things. Okay, so I guess we'll end now, and I think 6 o'clock is the opening reception, and I just want to let you guys know that it's exactly 1 hour, so go very quickly before everything gets over, and thanks for your time. You guys.